Next security mechanism is access control. Access control or authorization grant access permission to the specific resource. There are two primary approaches to access control that are used for APIs. There are two primary approaches to access control that are used for APIs. Identity-based access control first identifies the user and then determine what they can do based on who they are. A user can try to access any resource but may be denied access based on the access control rules. Second is capability-based access control. Capability-based access control uses special tokens or keys known as capabilities to access an API. The capability itself says what operations the bearer can perform rather than who the user is. A capability both names a resource and describes the permission on it. So a user is not able to access any resource that they do not have capability for. The next security mechanism is encryption. Encryption ensures that data can't be read or tampered by unauthorized person, either it is being transmitted or at rest. So data in transit or data in motion is data actively moving from one location to another, such as across the internet or through a private network. Data in transit is considered the most vulnerable type of data as it's transferred over the internet outside the security of corporate networks through potentially insecure channels such as cloud storage or third party service providers. Data transiting networks should be adequately protected against tampering and eavesdropping. This should be achieved through combination of network protection and encryption. Network protection denies attacker the ability to interpret data, and encryption deny your attacker the ability to read data. Consider an example of payment API, where customer submits his credit card details. If payment API request and response communication is not encrypted, it can be read by unauthorized person while it travels over the network. In order to attack data in transit, an attacker would need access to the infrastructure over which the data transits. This could take the form of physical access or logical access. If the attacker has compromised the software components within the service, it's more likely that the attacker would access infrastructure between the user and the service, as opposed to the infrastructure within the service. Encryption plays a major role in data protection and is a popular tool for securing data both in transit and at rest. For protecting data in transit, enterprise often chooses to encrypt sensitive data prior to moving or using encrypted connections such as HTTPS, SSL, TLS, FTPS to protect the content of data in transit. We also need to apply encryption to protect data at rest. Consider a scenario where we are storing credit card information in database or we are storing the scanned copies of customer documents. Conventional antivirus softwares and firewall are most common security measures used to protect data at rest. It is still at risk from both the malicious outsider and the insider threats. Compromising data at rest has large security impact on the organizations because the volume of information that can be stolen is higher than the data packets in transit. One of the best and easiest way companies can start protecting their data at rest by implementing encryption solutions, such as operating system native data encryption tools such as Windows BitLocker, disk encryptions, file or folder level encryptions, database encryptions. Encryption is also used in ensuring non-repudiation by using a digital signature. Each certificate is digitally signed by a trusted certificate authority or CA, and its hash value is encrypted with a private key also held by the same trusted CA. The sender of a message can use a private key to encrypt the hash of the document, giving its digital signature, which is attached to the document as it's sent. At the other end, the recipient may decrypt the digital signature using a public key by calculating the hash value of the document and comparing it with the document's decrypted digital signature, which is also the hash value of the document. The two may be compared to confirm that they match. With this match established, the recipient is able to confirm who the sender of the message actually is and which particular message was actually sent. Next security mechanism is audit logging. An audit log is a record of every operation performed using your API. The purpose of audit log is to ensure accountability. It can be used after security breach, as a part of forensic investigation to find out what went wrong, but also analyzed in real time by log analysis tools to identify attacks in progress or other suspicious behaviors. The last security mechanism we'll consider is a rate limiting, is for preserving availability in the face of malicious and accidental DDoS attacks. A DDoS attack works by exhausting some finite resources that your API requires to service legitimate requests. Such resources includes CPU time, memory, and disk uses, power, and so on. By flooding your API with bogus requests, the resources become tied up servicing those requests and not others. As well as sending large number of requests, an attacker may also send overly large requests that consumes a lot of memory. The key to fending off these attacks is to recognize that a client or a group of clients is using more than their fair share of some resources like time, memory, number of connections, and so on. By limiting the resources that any one user is allowed to consume, we can reduce the risk of attack. A rate limiter can either completely close the connections when the limit is exceeded or else slow down the processing of the request, a process known as throttling. When a distributed DDoS attack is in progress, malicious requests will be coming from many different machines or different IP addresses. It is therefore important to be able to apply rate limiting to a whole group of clients rather than individually. Network level DDoS attacks can be easy to spot because the traffic is unrelated to the legitimate request to your API. Application layer DDoS attacks attempts to overwhelm an API by sending valid requests but at much higher rates than a normal client. So as we discussed, there are two ways for the rate limiting. One is throttling, where we slow down the processing of the request for a particular user or the group of users. And the other is we completely close the connection to stop processing request for a user or particular group of users. So this can be configurable into the API gateway as per our needs. So security mechanisms in general. So how this security mechanism can be applied to our microservices to secure our individual microservices and ultimately securing our whole microservices deployments. A typical user sends a request through web or mobile clients. In order to protect request data, we should apply encryption like TLS or HTTPS so that no one should be able to get access to it while it in transit. So next, in order to protect the availability of our application and avoid our application running out of resources, we should add rate limiting to avoid the DDoS attacks. If a particular user or a group of users exceeds specific number of requests in a specified time period, reject the request from that user or group of users in order to keep our system running and available. Next, we need to authenticate users to verify users' identity so that no unauthorized person can enter into our system. Next, as a part of audit log, we capture who, what, and when, and from where about each request, which is very useful for forensic analysis and fulfill the compliance requirements. Next, we need to verify does the user having access to specific resources or data he is requesting for. He may have access to whole microservice or only to a specific operation or data. If we don't have access to requested data or the operation, we should be able to determine and reject request. In upcoming lectures, we will discuss each of the security controls in details and various patterns to implement it.